Here we are told the current through the terminals of two capacitors in series is given here. So we have that function of time for the current. We have capacitors in series. We're given initial values of the voltages for both the capacitors, which is important for us to do any calculations with capacitors. We need to know the starting voltages so that we can figure out what the voltage is going to be later on. We're being asked to find the total energy stored in the capacitors. So we're told that the voltage at the initial value of the voltage is 5 and 10. This initial value is T0, and we're going to go ahead and call that 0 seconds to go ahead and start our measurement. So this V of 0, that is our T0 that we're going to need later on. We're being asked about the energy stored in the capacitor, and we have an equation for that as well. The amount of energy stored in the capacitor depends on the capacitance and the voltage across that capacitor. Here we have two different capacitors with different capacitances. They have different starting voltages, and so they're going to have different energies. And so what's going to make more sense for us is to find the energy stored in one, find the energy stored in the other, and then the total energy stored is going to be the combination of those. So if we want to find the energy stored in these capacitors, we need to find their voltages across each capacitor. And if we know the starting voltages, we know the current being provided to the capacitor. They're in series, so the same current is going to supply both of them. We can use the current and the starting voltage to find the voltage later in time. As current flows to the capacitor, that current is acting as a change in voltage. So if we know the starting voltage and we know the change in voltage, we can find the voltage at any point in time later on. Here we're going to integrate in terms of T prime is going to be our dummy variable. And we're going to integrate from some initial point in time, T0, up to the arbitrary unknown T, so that when we plug in T, we'll have our voltage as a function of time. T0 here is going to be 0. We arbitrarily picked that. The C is going to be the capacitance of whichever capacitor we're looking at, and the current is going to be the function that we're given. So we'll find the voltage across capacitor 1 first. It'll depend on the capacitance of that capacitor and on the initial value of that voltage, starting from the initial value, which is 0, so we've plugged that in. Next, we're going to plug in the actual value for the current and for the capacitance. Notice a couple things here. I want proper units. I want volts for the units of my voltage, so I need to use proper units everywhere else. The capacitance is 2 microfarads, so I need to include that micro there to give me a value in farads, so I'm in proper units for capacitance. Recall that mu is 10 to the negative 6. The current is given to us in terms of microamps, so I had to use 240 micro here to give me proper units of amps for my current. The current is given as a function of time, but I've switched it from a function of t to t prime, so I can integrate with respect to my dummy variable. And then I've plugged in the value for the starting voltage there as well. Now I can integrate this exponential term. This part is a constant that will come out front, and I could use a substitution here to integrate this term. I've pulled this term out front. When I integrate this exponential, I'll get a 1 over negative 10 out front, and then I'm going to evaluate my function from 0 to t. I can simplify e to the 0 is 1, and I can do one last step to simplify everything. And so I found the voltage across the first capacitor as a function of time. I'll follow these same steps here. I'll start with the same equation, and I'll find the voltage across V2, plugging in the capacitance and the voltage for V2 here. I'll work my way through, complete my integral, and end up with a similar function. Now I found the voltage across the first capacitor as a function of time, the voltage across the second capacitor as a function of time, and so I can find the energy as a function of time based on these voltages I found and the capacitances that we were given. So I have my energy stored in these pair of capacitors as a function of time. It's 1/2 times C1 times V1 squared plus 1/2 C2 V2 squared. If I'm interested where the what the energy is as t goes to infinity, if t is going to infinity, that means that my exponential decay terms are going to go away. Those are going to go to 0 as t becomes very, very large. And what I end up with here is 1/2 times 2 micro times 2 squared is going to give me 4 micro. And if I have 1/2 times 8 micro times negative 2 squared, that's going to give me 16 micro. So adding those together, that gives me 20 micro joules in this case. Joules is my unit of energy. I know that I have joules because I used farads, I used amps to give me the voltages in volts, and so if I use all standard units going in, I'll get standard units coming out with the multiplier micro coming from the capacitances.